how does a machine actually do anything? From a robot arm lifting a heavy box to a plane adjusting its wings in mid-flight. It all comes down to the parts that physically get their hands dirty and interact with the world. So let's dive in and explore the hidden muscles that make our modern world move. So what are these muscles? I mean, we know our biceps move our arms, but what's the engineering equivalent? Well, the answer is a single, super important component that you interact with every single day, probably without even realizing it.
And here it is. It's called an actuator. Simply put, it's the part of a machine that physically changes its environment. It's the bit that turns a digital signal, like an electrical command, into real-world action. These are the muscles that make things happen.
And would you look at the variety here? When we hear actuator, our minds usually jump to motors and hydraulics, things pushing and pulling. But the definition is actually way broader. A heater is an actuator because it changes the temperature of a room. A loudspeaker, that's an actuator changing air pressure to make sound. Heck, even a simple light bulb is an actuator because it changes the environment from dark to light. But here's the thing. These muscles don't just act on their own. They can't just flex randomly, right? They need a brain to tell them what to do, and that system is called a control loop. It's basically how an actuator gets its marching orders. And this loop is just beautiful in its simplicity. First, you have a sensor that measures what's going on right now. Is the room too hot? Next, a controller calculates the error. That's the gap between where we are and where we want to be. Finally, the actuator springs into action to fix that error. Sensor, controller, actuator. This feedback loop is a fundamental concept not just in engineering, but literally everywhere, from our own bodies to the economy. It's a constant dance of feedback and response. And honestly, this concept is way more intuitive than it sounds. Think about being hungry. A sensor in your body detects low blood sugar. Your brain, the controller, sends the signal, hey, you're hungry. And then you, the actuator, eat some food. It's the exact same logic as your air conditioner. The thermostat senses it's too hot, the controller gives the command, and the cooling unit, the actuator, turns on. See? Simple.
Okay, so the actuator gets an order, but how it gets that order is absolutely crucial. It's not just about shouting, go. It's about the style of control. And a great way to think about it is to imagine the difference between two very different types of drivers.
First up, let's meet our reckless driver. In engineering, we'd call this proportional control. Their rule for driving is simple. The bigger the gap between you and the car ahead, the harder you slam on the gas. Full throttle, no questions asked. So what's the problem with this? Well, our reckless driver is only looking at one thing, the distance. They floor it to close the gap, but they arrive at the destination so fast that they can't make the turn. They completely overshoot the target. This overshoot is the classic telltale flaw of a purely proportional system. It's fast, sure, but man is it sloppy.
Now let's look at a much smarter approach, derivative control. This is our mindful friend. They're not just staring at the destination up ahead, they're also glancing down at the speedometer.
So let's put them side by side. On one hand, you've got the reckless driver, fast, aggressive, and always blowing past the target. On the other, you've got the mindful friend. They're way more predictive. They notice how fast you're approaching and say, hey, maybe we should ease off the gas now. This derivative control takes the rate of change into account, and that leads to a much smoother, way more accurate arrival at the target.
All right, so we've got our muscle, the actuator, and we've got our brain, the control system. But what about the raw power of that muscle? I mean, is more always better? Not necessarily. And this brings us to a really cool concept called actuator authority.
It kind of seems counterintuitive, doesn't it? Don't we always want the strongest motor, the most powerful brakes, the biggest engine? Well, not always. Sometimes an actuator can actually be too powerful for the system it's in or for the human trying to control it. This is where actuator authority comes in. And really, it's just a way of measuring how much an actuator can change its environment. For example, a big halogen lamp has way more authority to light up a room than a tiny little candle does. Simple as that. And anti-lock brakes are the perfect real-world example of why we sometimes need to limit that authority. Think about it. Your car's brakes are so powerful that if you panic and slam on them, you can lock the wheels up and go into a dangerous skid. The ABS controller actually limits your authority. It overrides you, rapidly pulsing the brakes for you so the wheels don't lock. It's a system literally designed to protect you from an actuator that's too powerful for a human to handle in an emergency. And this leads us to a really fascinating, kind of wild conclusion. In many of our most advanced machines, the biggest weak point, the biggest vulnerability, isn't the machine itself.
It's the fragile human sitting inside it.
This is the entire driving force behind unmanned vehicles, or drones, as we call them. Once you remove the human, you get to remove the heavy cockpit, the life support systems, the ejection seat. All that weight, cost, and complexity just vanishes. The actuators and control systems can now be designed purely for the mission, not for keeping a pilot alive. And the result is a whole new generation of lighter, cheaper, and way more capable machines.
And so, this leaves us with one final, huge thought to chew on. For about a century, we designed machines around the limits of the human body. But now, with actuators and control systems becoming so powerful and intelligent, we're taking that limitation out of the equation. So the question becomes, what are the new limits? What happens when the only thing holding a machine back is physics itself?